Okay, you're welcome to today's lecture. Just allow me to admit some of your colleagues, then I will share my slide. Okay, so you're welcome to today's lecture on CHM 316, Methods of Chemical Analysis. We started our lecture on gravimetry, and we'll continue from where we stopped, although I'll do a brief recap of what we did last week. I have so much distraction here because your colleagues are just coming in and I need to admit them before we start. I have several people to admit here. So let me do that and then we will start. Okay. So we'll continue on gravimetry. I did introduction last week and we talked about types of gravimetry and then advantages, disadvantages, and so on. So I'll do a recap a bit and then we continue with the rest until we can stop wherever it's convenient for us. So mention that gravimetry is one of the most accurate and precise methods for macro quantitative analysis. It measures the mass of materials. We have precipitation gravimetry as one of the types of gravimetry. Last week, we talked more of precipitation gravimetry, so I'll not stay much on that. So we have volatilization gravimetry. I didn't say much on that last week, so I'll just say something briefly about it now. So many of your colleagues, the students are just waiting to be admitted here, and I have to admit them. So just give me 1 minute to admit them in. It should not up to 1 minute to be done. Okay. So we have volatilization gravimetry. In this case, the analyte is separated from other constituents of the sample by converting that analyte into gas of non-composition, converting it into gas of non-composition. So then the weight of this gas serves as a measure of the analyte concentration. Remember, in precipitation gravimetry, you convert the analyte into precipitate, a compound of precipitate. But in this case, you convert the analyte of interest into a gas of non-composition. Then the weight of the gas is a measure of the concentration of that analyte. So in this method, what is done is that the analyte and its decomposition products are volatilized. I think I have to find out who that person is. Who is that? Please, can you mute yourselves? You're in the class. So don't distract us again. So in this method, the analyte and its decomposition products are volatilized. Then they're collected and weighed. Outside this way, there's an alternative way of carrying out volatilization, gravimetry. In this case, the mass of the volatilized product is determined indirectly.
All right. So,
Queen Ndak. Hey, Queen Ndak, are you the one making noise there?
So, I got a 3. So, say energy priorities. Do we get the NGA?
Energies are priorities.
All right, thank you very much. Energy priorities. Serious.
Okay. I've muted all those noisemakers. So let me just admit more of your colleagues, and we go on with the lecture. So I was talking about volatilization gravimetry, and I've told you the analyte of interest is converted into gas, and then the weight of the gas is taken, and that gives the concentration of the analyte. I say apart from doing it that way, you can also do it by indirect method. That is, the mass of the volatilized product is determined indirectly by loss of mass of the sample, by the loss of mass of the sample. Sample of the analyte of interest is volatilized into gas, and then the whole sample is weighed, and then the loss in the mass of that whole sample gives the mass of the gas that you're having interest in. I still have to admit more people here. Okay. So we have the other method also. I've told you about precipitation. I've told you about volatilization. And then this one is electrogravimetry. Electrogravimetry. In this case, the analyte is separated by decomposition on an electrode by electrical current. Decomposition of the compound on an electrode by electrical current. And then the mass of this product provides the measure of the analyte concentration. So that is that one. Then you have the fourth one, atomic mass spectrometry. Atomic mass spectrometry. Hold on, let me admit people. So the atomic mass spectrometry, in this case, uses a mass spectrometer. Mass spectrometer is used to separate the gaseous ions that are formed from elements that make up the sample that you are handling. So you use the spectrometer to separate gaseous ions that are formed from the elements that make up the sample that you're handling. So, sorry, this distraction with admitting. So, the concentration of the resulting ions is then determined by measuring the electrical current that is produced when these ions fall on the surface of an ion detector. First, you separate the gaseous ions that are formed from the elements. You use spectrometer to do this separation. You now have separate gaseous ions. Then the concentration of the resulting ions is then determined by measuring the electrical current of the ions that fall on the ion detector. Then the number 5 type of gravimetry is combustion, is using combustion analysis, and this is thermogravimetry. Thermogravimetry. Sorry, I have to still admit your colleagues. So thermogravimetry measures the changes in weight of sample with respect to temperature change. Changes in weight of sample with respect to temperature change. Either you heat the sample and the temperature changes, or you cool the sample and the temperature changes. So the change in weight of that sample with respect to temperature change is what you use to carry out this kind of analysis, to be able to know the concentration of your sample. So this technique is useful for studying the thermal stability of a compound, and also for studying the composition of materials, including even the decomposition of substances and phase transition. So you use this thermogravimetry to study how stable a compound is, and also the composition of materials. I want to use an example here for you to see. The example of thermogravimetry is that of the composition of calcium carbonate. The composition of calcium carbonate by changing the temperature. In this case, you heat it. So when you heat calcium carbonate, it undergoes thermal decomposition and releases carbon dioxide, forming calcium oxide. So in this case, you can see the equation there. You apply heat, and then the calcium carbonate that you had it in solid form. When you apply heat to it, you decompose it into solid calcium oxide with carbon dioxide gas being released. So in this case, if you're looking for the amount of gas there, you'll be able to know. You are looking for the amount of calcium oxide, you'll be able to know from this. Then let's explain what I just showed you. Sorry, I need to admit these people here. Well, I want to comment that most of you tried today to come in on time. So it's much better than the other day. And so I hope next time it will be much better, so that we don't spend too much time admitting people into the class instead of the lectures. So how does this work? I mentioned that you have the initial mass of your calcium carbonate, and then at the beginning, the sample consists of solid calcium carbonate. That's the initial one, and you weigh it. Then the mass measured, sorry, the mass measured by thermogravimetric analyzer is that of the sample. So now the heating, as the temperature increases, the calcium carbonate starts decomposing, and it decomposes into calcium oxide and carbon dioxide gas. So now you look at the mass loss. The loss in mass is what you're going to use to know the amount of your analyte. So carbon dioxide is lost, leading to a decrease in the mass of the sample. So the final mass is that of calcium oxide, which is in solid. And then it's this one that remains, that is a stable compound as a product at high temperature. So you'll be able to know, oh, this is actually the mass of calcium oxide in this calcium carbonate. So I talked about precipitation gravimetry in the first lecture. We did a lot about it, but I still want to touch some things here. I mentioned that it's the oldest analytical method to analyze, quantify analytes in macro amount, in large amount, not micro, and which involves weighing solid products in a pure form. It has to be in a pure form. And the solid products are usually from precipitating an analyte with a reagent. The reagent is called precipitating agent. So you have your analyte, you add precipitating agent, and it gives you the precipitate. So what I mean by weighing of solid pure product in solid pure form is that the precipitate that comes out has to be pure, and it has to be solid. Because if it is impure, it's not the amount, it's not the exact amount that you're looking at that you think you have. So it has to be the pure compound in the pure form. I need to admit people here. Okay. So, and so this involves selective separation of the analyte. The reason for the precipitation is that you have to selectively separate your analyte from the mixture. And then solubility, insolubility of precipitate is important. The precipitate has to be the one that is very stable, that is not going to go into solution again. So solubility is important in this case. And then followed by non-selective measurement of the weight of the resultant precipitate. Measurement of the weight, you just measure the precipitate as it is. You cannot select anything. Whatever is in that precipitate is what you're going to weigh. So that's why you have to have your precipitates formed in a very pure form. So, and then there are desirable properties of analytical precipitates. They have to be readily filtered. That is, to be in a form that it can be filtered well, not something that will clog the filter or that will be passing under the filter. So it means it has to be of good size. It should be readily purified. It has to be pure, otherwise you're measuring something else in addition. It has to be of low solubility, preventing losses during filtration and washing. If it is soluble, while you're washing, some of them will be dissolving into the solvent. So it has to be relatively of very low solubility. It has to be in a very stable final form, unreactive. Doesn't have to react with anything so that it will not form something else. And then known composition after drying or ignition. These are the desirable properties of analytical precipitates. Let me 1 second to admit your colleagues. Okay, so advantages of gravimetric analysis. I've told you about this in the last class. They are precise and accurate, up to 6 figures, especially when you're using analytical balance. They help in determination of atomic mass. You can use gravimetry to determine atomic mass of elements. They don't desire standards for calibration. They help in calibration of other equipment. You can use gravimetry. And this method is relatively very inexpensive. Though there are some errors that we can get there, but if somebody is very competent, the analyst that is very competent will be able to avoid some errors, because we know the sources of errors during filtration and during washing, and so one can easily avoid those sources of error. I need to admit people here. Okay. So there are disadvantages. Limited group of elemental analysis. Is not all elements that can be analyzed using gravimetry. Convoluted method, that is the accuracy or the skill of the analysts, very important. Otherwise, there'll be a lot of error. So, and it's only suitable for high concentrations. Analytes that are of very trace concentrations, that are very low in concentrations, cannot be measured using gravimetry. And it also involves a lot of labor. So you're doing everything manually, all the steps, it's a lot of labor and it's time consuming. Okay, the applications of gravimetry, we have it applied in chemistry, quantitative analysis of chemical substances. We have it applied in geology, when you're studying gravitational anomalies in geophysics. It's also applied in environmental science. You're measuring pollutants or contaminants in water, soil, and air. It's also applied in food and pharmaceutical industries, and you're measuring the quality of the products. Okay, still admitting your colleagues. Okay. So I want you, you'll do this class activity, but I don't have that time for you to answer questions now. So what I want you to know you should do is list some types of gravimetric analysis available. You go and practice that. List some types of gravimetric analysis available, which I've just shown you. Then give some advantages of gravimetric analysis. Go and try answering those questions. Advantages and disadvantages. Go and see how you can look at them. Okay. I need to see admit people. Okay. So precipitate, when we're talking of precipitation gravimetry, there are different types of precipitate. So we want to see those types of precipitate. We have crystalline precipitate. We have colloidal precipitate. Is not, both of them they're not all very good for gravimetry, but you will see which one is okay. Colloidal precipitate are small in size. They are amorphous. They are difficult to filter, whereas crystalline precipitates are large precipitate, defined shape, and easy to filter. You will state what type of precipitate from what I've shown you is suitable for precipitation gravimetry. I believe you can all answer that question from the last slide I just showed you. So try it and look at it. You should be able to answer it easily if anything like that comes in your exam. Okay. There are certain factors that affect filtrability and type of precipitate that is formed in precipitation gravimetry. There are certain factors that affect this, and we want to look at it now. After admitting these people here, we'll look at it. Okay. So the factors that affect precipitation or filtrability, when you want to carry out filtration of the precipitate, temperature of solution is one factor that affects filtrability. Why is it so? You know, at different temperatures, there are some compounds that will dissolve, that will go into solution. So you have to know what temperature is favorable. If you heat it, sometimes it could go into solution. And also solubility of precipitate in the medium in which it is being formed. That precipitate that you have formed, is it something that can go into solution in that same medium in which it's being formed? If it is so, then it will affect the filtration. Then pH of solution is also another issue. And then concentration of the reagents is another factor. The rate at which the reagents are mixed is another factor. All these, I have some explanations on most of this for you on some other slides that we are yet to see, that we'll soon see. So all this means that all these are related to what is called von Weyman equation, or what I've shown you up there, and we're going to use that to explain some of these factors. Von Weyman equation, otherwise also called relative supersaturation, RS, relative supersaturation, RS. So, I don't know why some of you are making noise. You're not paying attention in the class. Okay. Let me admit more. I didn't know you are up to almost 200 here. Okay. So, all these that I've just listed for you are related to the von Weyman equation, also called relative supersaturation, RS equation. RS equation. So let's look at the RS equation. So RS, relative supersaturation, is equal to Q minus S divided by S. Q minus S divided by S. Sorry. So where RS, you know, is relative supersaturation, S is equilibrium solubility of your precipitate. That is same thing as the molar solubility of the precipitate at equilibrium. Molar solubility of the precipitate at equilibrium. Remember that when you're talking of gravimetry, we're talking of stoichiometry also, which you're going to deal with the mole of reactant, the ratio of the mole of the reactant to the product, and you're using that for your calculation. So this is important. So Q is the instantaneous concentration. Is the concentration, also the concentration of mixed reagents before precipitation. Concentration of everything that is mixed, the reagent with your material, with your substance, your compound, everything mixed before precipitation. That is Q. Then the larger Q leads to colloidal precipitate. When Q is larger, colloidal precipitates are formed. Of course, that means that filtration is going to be difficult because colloidal precipitates are very tiny. And then when S is large, larger S leads to crystalline precipitate. This is a good one. So if Q minus S divided by S is large, that is, your relative supersaturation is large, it leads to small particles, that is leading to colloidal precipitation. So if your Q minus S divided by S, what I mean by that is just your relative supersaturation. If it is small, it leads to larger particles. So that will be more of crystalline, good particles for gravimetry. Sorry, I still have to admit more of your colleagues. Okay, so I hope you're following so far. So larger S and smaller RS lead to crystalline precipitate. So precipitate at elevated temperature. So you have to carry the precipitate, your analyte, at elevated temperature to ensure larger S and smaller RS. A smaller, yes, RS. That is the essence of what I told you in the last lecture about digestion, which you have to heat your precipitate right in the solution where it is formed to enhance a better stable precipitate. So this is why elevated temperature is useful to ensure larger S. Remember that larger S will lead you to crystalline precipitate, to lead you to high and lower RS and good precipitate for filtering. Still need to admit, I think some of these people are just having issue with their connectivity going out and in. Okay, so precipitate from dilute solutions. So these are the steps you should take to get good precipitates that can be filterable, that are in crystalline form. Precipitate from dilute solution, so that this will keep your Q small. So when your Q is small, this makes your S larger. And the precipitating solution should add it very slowly. If you remember, 2 slides I just talked about the rate of mixing when I was listing all those things that affect filterability. I mentioned pH and I mentioned the rate of mixing. So If you add your precipitating solution slowly, this will keep the S high. Of course, when S is high, the crystalline precipitate is formed that is useful. And also stir the mixture continuously. It will keep the S high. Precipitate at temperature near acidic end of the pH. The pH range, why do you have to do that? It's because many precipitates are more soluble at the lower end. What I mean here is that in many cases, acidic conditions, that is low pH, increases solubility of precipitates. Why is that so? Because the hydrogen ions that are formed, the hydrogen ions in acidic condition is much, and these can react with certain ions like hydroxyl carbonate and so on in the precipitate. And when they react, they convert them into dissolved species. So you don't have to carry out your precipitation in very low pH conditions in acidic because of this reason. So employ digestion technique. Like I mentioned, increase in temperature helps to keep your S high. And when your S is high, you can form easily crystalline precipitates that are easily filterable. I need to to admit people here again. Okay. Just give me 1 second. Admit your colleagues here. Okay. So you have to do your precipitation from homogeneous solution. Homogeneous solution, a well-mixed solution without, not heterogeneous. Homogeneous solution. Carry out your precipitation from homogeneous solution. Okay. Now, this is supposed to be a class activity. So list any 4 factors affecting the filterability or type of precipitate formed in precipitation gravimetry. I've just mentioned them: temperature, pH, rate of mixing, and so on. So you can list them. These are the things you should know. Then also using von Weyman equation, also called relative supersaturation equation, use that to explain how solubility and instantaneous concentration affects quality of precipitate. So you remember your RS is equal to Q minus S divided by S. So you can use all that I just explained to you to make this explanation. Now, practically, how can we vary RS? How can we vary S? And how can we vary Q to achieve better precipitation? I believe if you understand what I just explained to you, you will know what to do. See what to do to make Q smaller, and see what to do to make S higher, and so on. So I need to still admit people. Okay. So a recap, we have looked at types of gravimetry, precipitation, gravimetry, advantages and disadvantages, types of precipitate, factors affecting filterability of precipitate. So I believe you can remember all this. So we want to do mechanism of gravimetry. the steps in precipitation gravimetry. This just showing you, it's just like a seed is planted and it starts growing. Just like a baby is growing in the womb. That is how the precipitate nucleus starts, and it keeps building up and then getting big enough to make a good precipitate that is filterable. So how does precipitation occur? So we're referring to mechanism of precipitation. That is just to say, how does it occur? The way precipitation occurs, that is what we refer to as mechanism of precipitation. Step 1 is nucleation, like what I just showed you in the picture of those babies. So the aggregation of oppositely charged ions of the reagent to produce nucleus. That is the beginning of it. That is nucleation, which is the process of forming the smallest possible crystal of the precipitate. Smallest possible crystal of the precipitate is formed at the nucleation state. So a nucleus is the smallest possible size of a crystal, usually invisible to the eye. Now the second step is crystal formation. After nucleation, many more nuclei are formed. Several of them are formed, just like the first one is formed. Sorry. Number 3 is crystal growth. The first one is nucleation. Second step is formation of more nucleus. First one is nucleation, formation of nucleus. Second one is formation of several more. The third one is crystal growth. The formed nucleus increase in size. Just like the picture I showed you of the babies, the formed nucleus increase in size. When crystal growth predominates crystal formation, this leads to formation of precipitate with the following properties. When crystal growth predominates crystal formation, then you have the formation of precipitates that have these following properties. Is well-defined crystalline shape, large mean particle size, precipitates that are easy to filter, and precipitates that are easy to wash. So the nucleation I was just talking of, the formation of nucleus, these tiny particles here, we have the nucleus here formed. And the tiny particles come together to form the nucleus in the process of nucleation. Tiny particles, in this case, we have talked about the ions, positive and negative. The ions come together, and then in the process of nucleation, nucleus is formed, as you see here. And then from that nucleation, nucleus, you have several, I mentioned step 2, several nuclei are formed. Then the crystal formation now, the different nuclei, they come together and crystal is formed. And then the crystal formation, more and more, the crystals form, they come together, and then you have the particle growth as is shown here. So class activity. When crystal growth dominates properties of the crystal, what do you have? Do you have desired or non-desired properties? It's a question that you can look at and answer. It's very simple. I believe you can answer it. because I just talked about it now, that when crystal growth dominates the crystal formation, that you have desired properties that are stated there, which lead to the formation of what? Formation of what type of precipitate? It leads to formation of crystalline type of precipitate. So that is it. So what steps are needed to perform successful gravimetric analysis? What steps for the precipitation? Your sample collection is the first one, then collection and preparation, then preparation of the solution that dissolve your sample in appropriate solvent, then precipitation, that is adding your precipitating agent to your solution of sample, and you have the precipitate. Then digestion of the precipitate, that is by heating it. Then filtration, washing, drying or igniting, weighing, and calculation. I showed you how to do calculation the other time. I showed you an example of calculation in the last class. So we're not going to look at calculation here again. So after sample collection, sorry, let me answer these people and admit them in. I think some people are having issue with their network being disconnected and connected back. Okay. So, so the digestion here is explained here. Sorry, let me see. Maybe I skipped a particular step. Okay. So the digestion here is heating your solution that the precipitate is already in solution. You heat it at about 90 to 95 degrees centigrade. So the liquid or the solution where the precipitate is inside is what is called the mother liquor. So in this process, larger crystals grow at the expense of small ones. So digestion is also called aging or Ostwald ripening. Digestion is also called aging or Ostwald ripening. I explained to you the importance of digestion. When you heat the precipitate in the liquor, you heat it, it produces higher S for you, and that gives you crystalline or better filterable precipitate. Then the small particles tend to dissolve and re-precipitate on the surface of the larger crystals during aging. Remember what I just reminded you of now, that digestion helps to keep your relative saturation low. It helps to keep your RS value low. And you know, when you have RS value low, you have good crystals formed. So this is a picture of aging, just to show you this as an example to understand. So you have your crystals, the smaller ones are adding to the bigger one and they continue to grow with time. That is what is called aging. So the filtration is the next step designed to separate solid precipitate from the mother liquor. You now understand what I call mother liquor. I've already told you all this, so you can use different things. You can use porous sintered glass crucibles. You can use filter paper. The last lecture I gave you, I mentioned something about Bruckner funnel, where you can use vacuum flask and vacuum pump to force out the liquid and have your precipitate well separated properly from the mother liquor, ready for drying, for washing, drying, and weighing. So, of course, colloidal precipitates, now you know that they present problems to filtration because the particles are too small in size, and so they block the filter paper. And you also have to know that hydrophobic colloids generally filter better than hydrophilic colloids. The hydrophobic are the one that are water hating. The hydrophilic are the water loving. So the water loving, of course, has the tendency of going back to solution. Okay. Next step is that of washing. So you watch what solvent you use in washing, because some of them can end up getting the precipitate you formed back into solution. So, and here, example is washing. So when you select the particular solvent you use, example is washing silver chloride with water. This will dilute the counter layer and the primary layer charge. The counter layer and the primary layer charges are what are responsible for ion repelling and attracting ion at the surface and in the middle. So from the note here, you will see I've explained it much better. So wash silver chloride with an electrolyte like nitric acid that can be volatilized on heating. Ammonium nitrate is suitable for washing hydrous ferric oxides. So you select what you use in washing. Washing, I think I explained before. When you have your filtrate your filtrate, you have your filtrate on the filter paper. So you just keep on pouring the solution or the solvent onto the filtrate. That's your precipitate on your filter paper, and then keep on filtering it. You do that over and over until the mother liquor is completely cleared from your precipitate. So you know that what you're finally weighing is nothing added to your precipitate, but just your precipitate. And it's not something that will come and dilute the precipitate and reduce the concentration from what you're supposed to have. So the counter ion, I've already explained it. The primary and counter ion absorption layer, you can see close to the surface there. It's the ions are scanty there, and the other ones in the middle are coming together. And so simply the primary ion, which is called the stain, at the stain layer. Sorry, let me admit more of this thing is just disconnecting you and bringing you back, and so making it difficult for us to proceed straight. So the primary ions we're talking of in that in the scheme of what I just showed you is otherwise called the stain layer. It provides direct electrostatic interaction with the surface of the particle, contributing to particle surface charge. And the other one, the diffuse layer, the counter ion, helps to balance the charge and create environments where the particle is surrounded by a potential barrier. So together, the stain layer and the diffuse layer, they play a crucial role in stabilizing the colloidal system, and influencing the aggregation and sedimentation. aggregation and influence the coming together of the crystals to grow and form good precipitate. Okay. The drying and igniting. Dry the precipitate to remove water and volatile electrolytes from what you use, from the solution, from the solvents that you used in washing. So the ignition is done, it removes water of hydration and converts hygroscopic compounds to non-hygroscopic compounds. Hygroscopic compounds are those compounds that if you expose them, they will absorb water.
Okay. Are we cool?
Who is that person? Those are the people just coming in newly. Why are you making noise there?
They are noise making.
Okay. So we have an example here where you have your magnesium ammonium phosphate hexahydrate decomposed to pyrophosphate here. That's magnesium pyrophosphate by heating at 900 degrees centigrade. So you remove everything hydrated, every form of water, and now have a stable, dry compound. So that's an example. The purpose of drying and ignition is to help us have a final compound of stable and known composition. So the weighing, you use analytical balance, like I mentioned, to the 6 places, 0.000, so on. Use analytical balance. And before weighing, of course, after drying the precipitate, you need to put it in the desiccator to get it cooled before weighing. And of course, you have to weigh it several times until you get the weight that is a constant one that is not changing. You weigh it once, take it back to dry a bit, and then bring it back. If it changes from what it was, then it means it's still not dry. You keep on doing that until you have a stable weight. So calculation, I've already showed that to you, an example also. So now, list the steps in precipitation gravimetry. That's a question. Explain any 4 of the steps stating the importance I've just explained to you. So mechanism of precipitation, steps, here, calculations. There are errors in gravimetric analysis. So you should carry out your precipitation from homogeneous solution. So, yes, who is lifting hand? Success, Eze.
Eshima, please, can you bring back the slide for the class activity? You said list the step of gravimetry and do what?
Don't worry. You know, we're live on YouTube. And once we're done, I'm going to give you the link and you will see everything.
All right,
as
ma.
it is. Okay.
Thank you.
Okay. So certain errors that we encounter during gravimetric analysis. Sorry, I have to admit some people here again. I think it's a network thing. It's not new people coming in. It's people that have been sent out by network connectivity that are trying to come back in. Okay. So contaminants or impurities in precipitation, that is one source of error. Denny, you're raising your hand.
Yeah,
Yes,
I would like to be sure. Ma, are you going to release the slides to us, ma?
Yes, but I'm telling you that this is a live lecture on YouTube, which you can watch it over and over, and all the slides will be showing. So you will see everything over and over, even when we finish this lecture.
Oh, It's not
So
as
you
easy
want,
as reading the slide.
oh, okay, I will still give it to you. No problem. I'll send
Okay,
it to
ma'am.
your class rep. Okay. All right.
Okay, thank you, ma'am.
Okay. So so I said contaminants and impurities in precipitation. That's one source of error. So it's not going to give you what you expect. It's going to give you higher mass than what you're supposed to have because of the additional impurities. And especially also if you have co-precipitation, other things are co-precipitating along with your analyte, that's another problem. So peptidization is another, peptidization and supersaturation, those are other problems. So types of co-precipitation, we have occlusion and inclusion. Occlusion is a type of co-precipitation in which the soluble impurity or material is enclosed or entrapped within the crystal structure of the solid. Example, water with dissolved impurity trapped within a crystal. So as such, it acts as a seat of imperfection within the crystal. That's occlusion. Generally, occluded substances are distributed in a non-homogeneous or even fashion throughout the crystal. So in addition, the amount of occluded substance is greatly influenced by the conditions and manner of precipitation. This may also include holes and solvents containing dissolved impurities. So inclusion occurs when impurities occupy a lattice site in crystal, that is usually in ions. Isomorphous inclusion, when the ions or impurities of the same size or charge are trapped within the crystal lattice, like in case of potassium ion, in ammonium magnesium phosphate precipitation. So that also happens, and that is a bad source of error. So class activity, you should know how to differentiate between occlusion and inclusion. Go back home and know how to differentiate between occlusion and inclusion. You have it here in your notes, you can go and look at it well. Occlusion and inclusion impurities are difficult to remove. They cannot be removed by washing. Inclusion is not common, however, may be only corrected by removing the ion prior to precipitation. If you remove that ion before you carry out precipitation, okay. But if the ion is there and you carry out precipitation, this will occur to be trapped in the crystal. Occlusion can be removed by dissolving and reprecipitating the precipitate. You find out that something is trapped, we now dissolve it and reprecipitate it. And precipitation also from homogeneous solution. You carry out the precipitation from homogeneous solution. I believe you all know what the homogeneous solution looks like. You were taught in CHM 121, so you should know. And then digestion is effective in reducing the quantity of entrapped contaminants. That is inclusion. So digestion helps also to remove inclusion. So surface adsorption. What is the time? Oh, so sorry. I've shot the time. Sorry. we have already passed the time. So next class we will start from here. So I don't know who is coming in as I'm closing the class. Sorry, we have already passed the time. So you can go back.
Ma, we are enjoying the class. We are enjoying the class.
You enjoy the class. I have another lecture. So I have to leave for my other lecture. So till the next class that you can see, go and watch it. And we'll meet again in the next class. So I'll have to stop sharing. And
Sorry, ma.
Yes.
Ma, your YouTube channel, how do we have access to it?
And I'm